All right, everybody, here we are. We have a request to do Fall 2020 Test 4, Part 2, and I'll show you where we're at here. And this is the question here. We have a carbon that has a leaving group. It might not be obvious that's a leaving group, but that's the conjugate base of perchloric acid. The conjugate base of any of the strong acids is an excellent leaving group. And seeing as we're supposed to draw the Lewis structure of this leaving group, why don't we start right there? Perchlorate ion looks like this. Cl is the central atom, has double bonds all the way around, and double lone pairs on all the neutral oxygens, and 3 lone pairs on the anion. Very stable because it can resonate extensively. And what we have to do is our analysis here. And we'll start off with Rx. Make Rx green. Secondary, which means I do not have a conclusion. Secondary, the barrier for SN1 and SN2 is relatively the same. So we don't know. Nucleophile. We'll do nucleophiles in, I don't know, a new color. Purple. 2, new. This is an amine. HNET twice is an amine. It's not an anion, so it can't be a strong nucleophile. All of our strong nucleophiles have a minus charge. So this nucleophile is neutral, and because it's nitrogen, it's moderate. And you are at the same point you started. You do not know whether it's SN1 or 2. That's an even shorter way to say I don't know SN1 or SN2 if you want to do it that way instead of this way. And we better make a conclusion with our solvent. It looks like the solvent's missing, but we know better than that. When it looks like the solvent's missing, it means the solvent and the nucleophile are both the same molecule. There's just a very large excess of the nucleophile, which makes it also the solvent. Now, categories of solvent are polar protic, which is this one. Polar aprotic, which is not this one. Not when it hydrogen bonds. It's a polar protic solvent, which favors carbocations. That's SN1. My conclusion is SN1 because nothing else said anything else. Based on solvent this time. So we have to predict all of those products based on our conclusion of SN1. Keep in mind, the minor product for every SN1 reaction is an E1 reaction. So those will be some of the products, the E1 reaction. So where are we at? We have to figure out what the products are. We know we have to make a carbocation. We don't get points for doing the mechanism, but sometimes looking at the carbocation helps. So let's look at the carbocation. After that leaving group leaves, you have a cation over here. And because it's a protic solvent, we can make this cation, which is secondary. That's why we said SN1. And you realize that this cation has the ability to become a much superior cation with a hydrogen shift. Those shifts don't go away. And this, why is this a superior carbocation? Not only is it secondary, but it's also allylic. That's the equivalent of a 3.5 degree stability carbocation. That's very stable. I want the major product to come from this one, and we've got to show we know that. I'm going to shrink this down a hair, move these things down a little so I can draw the products underneath their labels. Now, carbocations, when they get a group and become a stereocenter, which is what's happening here, are always 50% R, 50% S. I almost forgot that in one of our videos, and a student made me come back and put a comment down, and I'm thankful for that student. NHET twice. That's a nitrogen with 4 bonds. Normally, cations aren't very stable. This one is. Ammonium ions are quite stable, and you have to tell me you know this stereocenter. I'll use this symbol here. Whenever I use that symbol, it's not for stereocenter, it's for this, 50% R, 50% S. If I write it once, then I can just use this star over and over, asterisk, whatever you want to call it. That's our major product. That's the SN1 product from this superior cation. There's also SN1 products from the inferior cation. Same story. It's a secondary carbocation that's becoming a stereocenter. You're going to get HNET twice here with the same 50-50 mix of R and S. Show me you know that. Now, the minor products arise from the elimination reactions. From a carbocation, you can remove a beta H from here or here. That's 2 different products. This one, you can only remove a beta H from here because you're not going to remove another H here to make a double bond and a double bond with an sp carbon in it. You can't do that in the small ring. Plus, just don't remove an H from an sp2 carbon. Take it from an sp3 carbon that's 1 carbon away. So you can do it there to make that product. You get the same product taking this H and removing it with a base instead of rearranging here. Make a double bond there. And I kind of like that double bond better than the other one because it can resonate with the existing double bond. But in this question, I don't care which one's the most minor and which one's the second most minor. Didn't ask for it. I'm not going to ask for it next week. You don't have to tell me there's more of this one than this one. But these can't resonate with each other and this can. That's why. We got our Lewis structure for perchlorate. Oh, we get extra stuff. I don't want it. I can't move it. I am just going to say the answer for Lewis structure is right there. And that is the end of that one. And before we come back for our next segment, do you have another request before we come back?
Could we do part 4, number 5?
Absolutely. We're going to come back with same test, part 4, number 5. We'll have it all ready. See you soon.